Okay. Before I forget, the exam, it's coming up, like it or not. So my plan has been to see how much progress I can make, whether I want to bring the exam still within the semester or have it straight outside. Looking at my calendar and looking at the material, my plan would be to have the exam on the last day of the semester, which is a Friday. And I think it's the 4th. Of course, you'll get an email about this. I just want to announce this now. Yeah, that would be Friday and actually probably 2 days, Thursday afternoon and Friday afternoon, because we can handle it in 2 afternoons. So that would be still within the semester and wouldn't affect any plans that you have, perhaps for travel outside the semester. But even if you're not here physically, the exams will be online. And the idea is that you will have to explain the solution to the homework problem to one that we select on the spot. And that means you have to have the ability to share your screen and some ability to write on the screen. I mean, Zoom does have a writing function, not extensive. If you have access to a tablet, you can do what I'm doing, just connect with the tablet. I'm actually connecting both, as you may have seen. So we don't want to be in a situation that I'm asking you to just scribble something. So it won't be extensive. If there's a surface behind you, a blackboard, like I have one, right? Although it's a fake one. If you have a real one behind you, you can write on the wall of your apartment. Of course, you may get in trouble afterwards for that, but that's also an option. So some way of writing. Again, it's not going to be extensive, but we may have, it cannot be purely verbal either. Although it actually, in most cases, it ended up being purely verbal, but just in case we have some sort of misunderstanding, it helps to be able to write. Okay, on that note, as I understand, about 15 people are signed up to take the exam, but only about 13 people have been turning in homeworks. Without the homeworks being turned in, you will not be able to take the exam, because the homework is vital to the exam, given that the exam is a discussion about the homework. So I'll send an email to that effect, but that has always been a prerequisite for the exam. So maybe just 2 people just didn't bother to unregister from the exam, but only people who have turned in all their homeworks can take the exam. Okay, so again, I'll send an email to that effect. Any questions about the exam? I anticipated usually it's 20 minutes per person, and then you'll get a scheduled one exactly to log in, and we're done in 20 minutes. You obviously have to have all your homeworks that you turned in at hand so that you can share the screen and explain your solution. Yeah, any questions? Go ahead.
Yeah, maybe just a very quick one. So this will just purely be the homework, none of the examples touch or the, because
I mean, but to be honest, the homework is an excuse for me to ask also questions.
Okay.
But yeah, because I ask you, why are you doing that? Because we all agree that if all you need to do is just take a PDF file and read out for me what you see there, then it's not much of a challenge.
Of course,
I might ask why you do that. But it's not in the format that, okay, we're done with the homework, let me ask you a few general questions. It is focused on that problem in the homework. That's why I hope to be able to done, and that was always the case, we were done in 20 minutes total, with some people much earlier than that.
Yeah, so it's not, for example, the practical experiments that were discussed sometimes that won't be needed to remember how these things were conducted, or what was the history.
I mean the derivations or not, but you're expected to know the material, right? And that's why I'm not announcing which homework I'm going to ask you to discuss, because the homeworks, you should be able to discuss each and every one of them, each and every problem, right? But I mean, obviously, my expectation is that people would also go through the material when they prepare for the exam, because I would be them asking questions about the material as well. But it will be guided by the exam, by the homework.
Maybe another small question.
Yeah.
If I want to write on my laptop, I need to flip it over, right? So is it a problem if the webcam's not on at this moment because it will only show my roof?
No, that's not a problem. No.
Okay.
No. Okay. All right. So where's my screen? It has. Oh, okay. It's here. So what did I do last time? So I finished the general discussion of normally hyperbolic invariant manifolds, and I said that so perhaps this week I'm able to just give you a quick idea as to how one actually proves these invariant manifold results, because so far we've been listing them. Okay, now to prove them in the highest generality that I've listed them for normally hyperbolic invariant manifolds, that would be, that would be a whole semester and potentially more to fill in all details. So what I thought, I would just give you what the three main methods are, and I would walk you through the proof of one of them, perhaps the simplest one, because even though the more involved invariant manifold results are more involved to prove, the basic idea is actually very similar. So I think by just from the simplest one, you would already get a very good feel for how these results are proven, and not because you're a mathematician and you absolutely need to, but I feel that I also certainly learned a lot from this when I first saw this proof probably decades ago. I worked through it, so I give you basically a version that hopefully is accessible, and there are techniques that I think you will find useful. I also wanted to just show you the three main methods that one generally can use to prove invariant manifold results. There are actually, there's a couple of more maybe, but these are the classic ones. Lyapunov-Perron method, which is basically a conversion to the problem into an integral equation. And as you will see actually today, that's very efficient when you look for a manifold which is expected to be a graph over a particular subspace. So it doesn't have any issues of folding over. When it has an issue of, so then that goes to an equivalent integral equation formulation, and the manifold turns out to be an appropriate fixed point of an appropriate operator defined for the integral equation. Hadamard's method, or the graph transform method, which is also the one that Fenichel used in his proof, is more of a global method. So it's enough to have local coordinate charts. And again, it would be more appropriate for a manifold that has a general shape. And it's really just only concerned with the general Lyapunov type numbers that we were discussing. If this is a manifold, then how exactly are the stretching rates along the manifold relative to the stretching compression rates normal to the manifold. And it doesn't matter, because it doesn't work with a global integral equation. It doesn't matter if you have to keep changing from one coordinate chart to the other, because ultimately it's this asymptotic number that matters, the Lyapunov type number. Okay, and what this does, the graph transform itself, you do have to have an environment in which you establish from these numbers there's this strong compression in one direction, and the overflowing invariance will guide you in this direction, in the other direction. And basically you take candidates in this global coordinate system, you apply the flow map to them with a fixed time. This is for autonomous systems. And basically the estimates that you can get from the Lyapunov type numbers from the assumptions of the theorem will ascertain that when you apply the flow map to a graph candidate or a manifold candidate, then it will get squeezed in this direction, it will get stretched out in that direction. So you do apply the flow map to it, and you cut off the part that's overflown. So as a result, because you have made it even flatter in the vertical direction, if it was a graph to begin with, then it's still a graph. And it's still, because of that cutoff, still defined over the same domain. So you took one graph over a given domain and you mapped it into another graph. And then you do the same procedure over again. And the idea is to show that this actually converges. So this will actually converge to a fixed point, a fixed graph, which no longer changes. And then that's an invariant manifold. Still may be overflowing, but the part that's over this domain is invariant. So this was Hadamard's method, and as I announced, there's a third one, which is quite nice, but it doesn't buy you that much, and because it doesn't give you smoothness. And these just generally, I think, refer to these as topological methods in the notes. And I mean, what the main example of such topological method, some call it the cone principle, others call it the Wasewsky method. And it is about cones. So basically, in some coordinate system, you need to know a little bit about the system. So in some coordinate system, maybe I actually draw sort of a quasi 3D figure as opposed to what I have in the notes, just to, because I just mentioned the cone principle. So actually, in 2 dimensions, I have a picture in the notes which explains the same thing in this context. In two dimensions, a cone is just a triangle. But I just realized that might not give you a general idea. So you have 2 sets of coordinates, and I'm just showing them now in an extended setting where you still have 2 sets of coordinates. And in fact, what I call here x coordinates, it can still be, you know, an n-dimensional variable, and the remaining part still can be m-dimensional. Okay. But somehow you're able to do estimates. Typically, you're able to do those estimates because you're close to the origin. That would tell you what happens to trajectories that enter an appropriately selected cone. Well, the types of estimates that you will be able to do, say, close to a saddle point, is that if they stay, that sooner or later they will leave. And so as long as they stay close, since the system to the saddle point, since the system is fundamentally linear in a neighborhood, a linear leading order term plus high order terms, you're able to argue fundamentally that the y coordinates, generally speaking, for most of the trajectories will tend to grow. So you will tend to get out of this cone in general. So Wasewsky has as a general result for cases like this, is that if you look at the points that you look at entry points here of this face of the cone, then he calls, you know, those points W, I think upper or lower index eventual. So that's in fact we look at all points that enter here, and W eventual is a possible subset of all the entry points that eventually leave the cone. And he has this, actually for general sets, not just for cones, that he has this category that you place a set in a general dynamical system which is autonomous. And you look at the surface of that set, the boundary, and you look at the part where trajectories enter, and just generally speaking, define the set of points in general, which will ultimately leave that set in some finite time, ultimately. And so that's one category. And the other category would be the points that immediately leave. So the points that actually in no time, whenever you just run the time, just ever so tiny fashion, then they immediately leave. So these would be the that immediately leave. So these are 2 sets in general. And Wasewsky has a principle that under certain conditions establishes a relationship between these 2 sets. Namely, he says that if you take the mapping that takes the points of the set who will eventually leave, so these are basically, think of these as the incoming points, and maps them to the point where they leave, which therefore maps them into the immediately set, okay? And again, he has that under impressively very general conditions. I just have drawn a cone, but generally speaking, he puts sets of dynamical systems in the phase space and talks about this mapping. Then the statement is, which goes by the name of the Wasewsky principle. The statement is that this is a C0 mapping. So it will be, it may not be a smooth mapping, but it will be a reasonable mapping. So if you ask, I know that a point is just entering right now and will eventually leave, and I want to map it to the actual location, to the point where it does leave, then it doesn't really matter what happens in between. This is a continuous mapping. Okay, and therefore, in this particular case, it turns out that all conditions of that are satisfied for the cone, and that gamma mapping is something that, say, takes this. I shouldn't use a different color. So it takes one of these points, say this one, let's just say, and maps it to that one. Right, so that would be the action of gamma right there. So you can imagine that for each and every incoming point, there's an outgoing point. And the way to phrase the existence of a stable manifold in this sense would be, is there something that never leaves? Is there something that just remains trapped in the cone forever? Because then it turns out, using the estimates that you can get from linear system, that the only way that can happen is that it must actually converge to the saddle point, because everywhere else you will have drift that will push you out. The drift will be, of course, weaker and weaker, and will take longer and longer to kick in if you're closer to the saddle, but ultimately you will be flushed out unless you're converging to the saddle. That's the next estimate in this method. But the basic principle before you get to that estimate is this Wasewsky principle, which tells you that this mapping is C0. Now, how would that help you? Well, in this particular case, I look at the sole incoming surface here. Maybe I switch to a thinner shading. And the statement would be that if you, I forget what he does on the boundary, but let's just look at this open set excluding the rim. This is then an open set like that. So if all trajectories just leave without ever converging to the saddle, so everybody basically gets flushed out. So in other words, there's no stable manifold. Then this open disk would be mapped into what? Just follow the points. They would be mapped into this subset of the cylinder, right? Now, they cannot be mapped into the saddle point because the saddle point is a fixed point right there. So they would certainly not leave from there. So if all of them were to leave, then you would have an open connected set like this, a disk, mapped into, when you straighten this out topologically, what would you get? Well, you would get this, because you have to take out the tip of the cone. So the statement would be that your disk gets mapped into another disk with a hole in it. And a continuous mapping cannot do that, right? So that means, so that would be then a contradiction with the Wasewsky principle. And the result of that, there exists an initial condition that never leaves the cone. So this is just a sketch. Obviously, this is not a proof, just basically gives you a flavor of that. So maybe somewhere here, you know, somewhere there has to be an equivalent of that dot that you have, that hole in the target. You have to have that hole here as well, which means that you can't say that all of these will eventually leave. There has to be one, actually precisely one exception. And that exception is then a trajectory that is supposed to be traveling, you know, there. Now, this is a topological principle because we know very little about how that location changes when I then take closer and closer, smaller and smaller cones. So we actually know very little about the shape of that trajectory. And at the end of the day, and how that connects potentially to another component here. So this is the reason why this doesn't give you smoothness, only continuity. Continuity we can establish, but gives no smoothness. So this gives existence of invariant manifolds. But no smoothness. But I always found it very beautifully elegant in its simplicity and purely topological, and barely any equations involved. There's the additional step that, you know, once you say that there's a trajectory, there's precisely one initial condition that never leaves. There's one more step from there to show that if something is stuck in this cone for all times, then necessarily it must converge to the saddle. That involves estimates, and that's where you start using the actual form of the dynamical system. But all in all, this is less effort than the other two methods. It also buys you less, to be honest. But if all your interest is just the existence of a stable manifold without actually showing that it's a manifold, if you're just happy showing that it's continuous, then this is fine. That would be it. So the one technique that I'd like to talk a bit more about, because I think that doesn't have the complications and yet it's sort of a rich in different steps, would be the first one. And I've written out the notes, and I'm just going to walk you through as you were to walk me through your homework problem in the exam, right? Because I think that, you know, I want to save some time in writing. And I think this is doable in this fashion. So I copied everything except I forgot to copy the title of this now. So existence of a stable manifold locally to the origin, to a saddle, and in 2D. Simplest setting. So this setting looks like this. You have a two-dimensional ODE. Okay, here's the dimension. It's autonomous. F is a general nonlinear function. And for simplicity, I assume that the origin is the fixed point. So I shifted coordinates to the origin to make life simple. My assumption is that this fixed point is a saddle point. Namely, when I look at the spectrum of the linearization, so I linearize, I take the Jacobian of f at 0. This will give, this is the spectrum, the collection of its eigenvalues. Then I have a negative eigenvalue, which I will call minus lambda s. S goes for stable, but itself, this will be a positive number for simplicity later on. And there's a bit of a confusion here, so let's make that lambda u. So there's that, and there's the unstable one. And corresponding to these, there's a stable eigenvector, say normalized, and there's an unstable one, normalized. Everything is real in this setting. Okay, so it's a two-dimensional system, and I have a saddle point. And I have normalize these, and they are real. Okay, so really just think about your good old saddle point. Probably looks like this, right? So except that I will line it up in a way, just in a second, that this will be the first coordinate, the stable one, and the other one will be the unstable one, just for convenience. And the objective would be to prove the existence of a local stable subspace. So that would be then the continuation of a local stable manifold, right? So that would be the continuation of what you see here. ES would be the stable subspace. We talked about this in Online Dynamics 1 and used it ever since. And already in that course, I claimed that there's a nonlinear continuation of that when you add the nonlinear terms, right? Which would be the local stable manifold. Indices are interchanged. So S is above superscript, log is lower script. Okay. So step one, and this is specific to the procedure that you generally have in the Lyapunov-Perron method, which again will be a conversion to an integral equation. That's what I'm working on, integral equation. So how do I go about that? So at the heart of that method, as I say, you have to have good coordinates. And by good coordinates, we will mean that for the manifold is a nice, at least locally, is a nice graph over the directions that I understand well, the stable and unstable directions. Okay, so that means that I will change coordinates to those. So how do we change coordinates to a prescribed set of axes? I take the vectors aligned with those axes. This is something we learn in linear algebra. Put them together in this matrix. They're column vectors, and I will use this T as a transformation matrix. This is the coordinate change, and the new coordinates I will denote by Y. First coordinate will be called Y, S for stable. It will align with the stable eigenvector. The second coordinate will be YU, aligns with the unstable eigenvector. So this is the picture that we're aiming to get. So in the new set of coordinates, you know, this will be YS and this will be YU, unstable. So we know that under the linearization, these are invariant subspaces. So this is the dynamics. So this is the linearized dynamics. So the linearized dynamics is saddle point. So indeed, when I go through this change of coordinates, how do I do that? X dot is t times y dot, right? I just differentiate this with respect to time, and I need to express y dot as a function of everything else because I want to have an ODE for y. So that's going to be t inverse x dot. The inverse exists because these vectors were linearly independent, given that they are eigenvectors corresponding to different eigenvalues, which are always linearly independent. For x dot, I had an equation here, so I plugged that in. But I've already Taylor expanded the right-hand side of that equation. This was the linearization of that equation. It's Jacobian of f at x. Remember, the 0 is the equilibrium plus second-order terms. So when I work this out, I will have the usual transformation of the linear part t inverse times the Jacobian times t plus quadratic terms. And the way I've engineered this transformation must diagonalize my linearized matrix. So I should see the eigenvalues showing up here in the diagonal. That's exactly what I have, and that justifies this picture here. Right. Of course, these I didn't write out because I didn't need them at this point, but I know that they are there. When I execute a second-order transformation on the x terms, that linear transformation, that doesn't change their order. So I will just refer to this vectorial function as GSY, GUY, the two together, right? That's the order x squared. But instead of x squared, I plugged in TY. That doesn't change the order. So these are the two components of the nonlinearities in this coordinate system. The nonlinearities are A, nonlinear, B, they will generally couple these two equations, right? That's why they're functions of y. As at linear order, you have the decoupling, but the nonlinearities couple the equation. So this is your nonlinear equation. These are for the y squared in the new coordinates. And just to make sure we know what that means, because here it will be important for the estimates, when I write order big O y squared by definition, or by implication, because some don't take this as a definition, but I think that's most people take this. What is the meaning of big O y squared? Big O y norm squared is something that remains bounded even if I divide it by y squared and take the limit of y going to 0. Excuse me for 1 second. So that's the meaning of big O. This is true for both. That's what I meant to write here. So both, no, sorry, that was U. It was actually, it's just, I found it difficult to read. So both for the S and the U, when I divide these quantities by y norm squared, and I take the lim sup, it's still less than a constant, right? So for a linear term would not satisfy that, right? A linear term would blow up there. Something to the 1/2 would also not satisfy that. It would blow up. But because this function was smooth to begin with, which I didn't say, but I should. The next term in the Taylor expansion is not some funny thing, but it's, in fact, for that C1 is enough, but let's make it C2. But it's a quadratic term. Now, that's good, but all I did is just change coordinates. Now I start looking for the manifold, which I envision as a continuation here. So that's what I'm looking for, hoping to establish its existence. In fact, I've stated that it exists, but is that really true? Can I have a nonlinear continuation of that? So this would be the nonlinear continuation of ES, which would be the stable subspace, which is here. The procedure that I'm describing here will work equally well for the unstable one, but you have to reverse time. In fact, once you've done it for the stable, you just rescale, change time in the differential equation, T2 minus T, and you're done for the unstable one. Because somebody is a stable manifold is in forward time is the same person's unstable manifold in backward time. So we need to have a target. So what's that? When I say, well, I'm looking for something which is blue and tangent and doesn't fold, and that's not something we can really work with on this equation, how you implement that. So you need to have a definition. Now, the classic definition of a stable manifold is easy to state, and I argued, several times why it makes sense and how it makes sense, is that it's a unique property to be on a stable manifold in a saddle point, because everything else goes to someplace else. I don't know where they go, but I know that the stable manifold of a saddle point is such that if you take any point on this and apply the flow map to it, then as the time in the flow map goes to infinity, you will be going to the saddle point, and that's unique. There's no turning back here, right? Or if there is, then that's because you're connected to that red curve on the other end, okay? So this uniquely defines the stable manifold. It's a curve. We don't know that yet. Sorry, stable set to begin with, and then we establish that it's a manifold. Now, why is it not helpful here? This is a good definition, but this equation is a puzzle. We don't have a full understanding of what the solutions of these equations do. I mean, you may have 100 other fixed points here, limit cycles and everything. If we knew everything about the flow map, that I could sort out the points that have this property, but I don't. So this is not an actionable definition. It's a good definition in the sense of defining what the stable manifold is, but it's not helping you in terms of constructing it. You can't take action based on this. So we need something that's more specific, or something that I can try to enforce on this equation directly without knowing all its solutions. And that's really because I really have no idea what the trajectories do, right? So there's an alternative characterization of the stable manifold, but unfortunately, as we know now, it only works in linear systems. But I can just say, look at this linear system here, that what distinguishes the stable subspace, which in the linear system is the stable manifold, is that everything else becomes unbounded. It's only the initial conditions in the stable manifold that remain bounded in forward time, right? So that sounds like a grand idea. Why don't we adapt that to the nonlinear setting and require that I'm looking for solutions of this equation that remain bounded for all times, and that will be my stable manifold. Slight problem with that again, who knows? I mean, I may well have another equilibrium point which is stable, even a spiral. And of course, everything that runs into that will also be bounded. I may have a limit cycle somewhere here. Those will also be bounded. It doesn't mean, however, that they run into the saddle. So that's not good enough. I just have a little figure here that even if you have, a local geometry like this, something that takes off near the saddle might just run into another fixed point. So what works well for a linear system and for this geometry, boundedness versus non-boundedness, although it's a very attractive way of defining something, because on that you can do analysis. Why? Because you can do estimates. Without knowing the flow map, hopefully you will be still able to estimate its action on initial conditions. However, just because something is bounded, it would work in a linear setting. It doesn't necessarily work in a nonlinear setting. You would have to know a whole lot about the system and guarantee that everything that passes by this saddle point goes unbounded. Who knows that, right? However, can we still take this idea, because analysis is very developed when it comes to estimates. I mean, the whole nonlinear analysis essentially is all about doing estimates. So can we still push this problem in that direction? And this is really the big idea of this approach, due to, who was that, Lyapunov-Perron, is that, you know what, let's change the system a little bit. So let's change the system smoothly outside a small neighborhood so that there it becomes linear. That seems like a bad idea to begin with, because why am I changing the dynamical system? Then I get a different dynamical system. But the idea is much deeper, and it actually, if you think more about it, then it starts making sense. Namely, just for simplicity, suppose that I do that change outside the box. So here were my original coordinates, right, that I so nicely kind of aligned with the stable and unstable subspace. So this is ES direction, EU, okay? And I know from much deeper theorems that near this hyperbolic fixed point, that's Hartman-Grobman, the dynamics is topologically conjugate to the linear dynamics. So there will be no surprises really, no major surprises within this little box here, because my dynamics is topologically conjugate to the linear dynamics. But that's about orbit pieces, not about asymptotic behavior, right? So what if I leave the system, unchanged here, and I just let it be nonlinear and do what it does, but then start somehow tinkering with the system outside? This will, and turn it into linear. If you turn it into linear, why does that help you? Because for this altered system, if something then, a trajectory leaves this area and then starts living in the linear world, then all of a sudden, bounded versus unbounded becomes a major difference. So now I'm looking at this new system, which is, inside the box is linear, outside nonlinear, outside the box is nonlinear. So that pertains to both pieces of the trajectories. So where it really matters, because this is going to be a local construct anyway for the local stable manifold and not the global one, where things are really happening in terms of their relationship to the origin, I'm not changing anything. But in terms of the asymptotic behavior of the trajectories, it's asymptotically linear in both time directions. Okay, so therefore, all of a sudden, I can make an asymptotic statement about bounded versus unbounded. And it will then presumably pick out the stable manifold that I want, at least the piece. Now, I will know that whatever I get out of this is only valid here because here I haven't changed the system. Okay, but hey, if I get a stable manifold just here, that's good enough for me, because then I know that this piece this piece agrees with the dynamics in the original nonlinear system because I never changed the dynamics here. So I can just pick the initial conditions here and run the flow of the nonlinear system backwards, and it will give me a manifold, right? So this local view turns out to be very beneficial in a lot of situations. So the key observation is that all trajectories that are missing the local stable manifold, which I hope to be there, will be therefore passing through this box, and asymptotically, because they are entering a linear system, there will be no funny business of these going to a limit cycle or a fixed point. It's a linear system outside, so they all become unbounded automatically. So it will be a good characterization of looking for the local stable manifold in this altered system as the set of points in this little box. But I'm considering the whole system, but whole altered system, but I'm only defining the manifold local is the set of points there such that when I act with the flow map of the altered system on these initial conditions, then as time goes to infinity, the outcome of that, the trajectory, will remain bounded. Okay. And again, all of a sudden, this makes a lot of sense because anything that leaves that box goes unbounded, and then anything that stays, the only way it can do it turns out, well, that will be that's my definition of a stable manifold. You could say, one could arguably say that, hey, this sounds like a lot of work. Why don't I just do that? Why don't I just, estimate what stays in the box and what doesn't stay in the box? Why do I go for bounded versus unbounded? Now it turns out, and you're absolutely right, but it turns out that's a much harder thing to do. So this bounded versus unbounded turns out to be much easier done. And that's what I want to convince you about. Sometimes I push something and then I lose some brightness on the screen, and I don't know how to get that back. Because I'm on maximal brightness, so I have no idea. Maybe I unplug and replug. Yeah. So how do I go about this? By the way, the minute I define such a curve, it's invariant by definition, because if for some initial condition, the trajectory from that, starting from that, is bounded, then any finite time image of that initial condition has the same property, right? So if I start from here, and what distinguishes that initial condition is that the outcome of me applying the flow map remains bounded, then certainly for any point along its track, the same property holds, because I know that ultimately I'm remaining bounded for all times. So then anything on the trajectory will have the same property. If I start from those points, they remain bounded. So therefore, this curve that I identify this fashion, only about talking about its boundedness, will be an invariant curve by definition, because you will never, if you start from initial condition that remains bounded in forward time, then no matter where you check in between, that definition still applies to you, that you will be remaining bounded forward time. That's why it's an invariant curve. So how do I go about this? So I need to do a smooth change of the system. And this is one of the reasons why I'm showing you this, that this is actually doable. So you can define something, even though this looks like, oh, it's not starting out well because it's already a non-smooth domain. But it still turns out to be doable in the following sense, is that in this little box, I will leave the system unchanged. The size of that box will be delta in all directions. and I pick a bigger box whose size is 2 delta. So all over you have 2 delta minus 2 delta minus 2 delta. And I take the original right-hand side and multiply it by 2, I guess you would call them, maybe in computer terminology, masking functions. But you multiply them with 2 masks. One of them will cut off the nonlinearities in the ys direction as a function of ys, and the other one in the yy. Their product I call psi, and these individual I call psi delta, psi delta. Now I feed the psi deltas, here's the mask. These are called C infinity bound functions or mollifiers in analysis. They're constant within the delta minus delta area. So it's constant, and not only is it constant, it's equal to 1. So it's not doing anything when I multiply the right-hand side by these two. They're not doing anything. But once you are past this boundary, they start decaying, and they do that fairly fast. They decay down to 0, and by the time they reach 2 delta, they are dead 0. Okay, and that multiplication turns this nonlinearity off completely in the green domain. So therefore, in the green domain, this term will be out when I multiply that term, and you revert to your linear system. Right? That is just the same linear system that we started out with. So it's remarkable that such functions exist, that you can do this. Of course, you could do this in a non-smooth fashion like that, right? There's no big deal. But the minute you do that, you lose the nice properties of your flow map, your ODE, and everything. Also, you don't just want to do it in a crude fashion so that you match first derivatives, because that will then backfire later when you want to get the maximum smoothness for your manifold. And when you have just only the derivatives matching here up to some finite order, that will affect the modified system. It will have just some finite smoothness. Therefore, you're losing smoothness because of your construct. Now, it turns out that can be solved, that problem by picking this function in a C infinity fashion. So there are functions that do this, and they are C infinity. So that means that all their derivatives vanish here, all of them, and all the other derivatives vanish there, and still they nicely connect the 2 points here. They are C infinity, but not analytic. They cannot be analytic, because if you have an analytic function whose derivatives, all of them, vanish, then it means that its Taylor series is identically 0. So in a neighborhood of the point where you calculate the Taylor series, it should be dead flat 0. And this function isn't. It's identically 0 in one direction, but it's taking off in the other direction. If you see a function like this, by inspection, it cannot be analytic. Okay? It can be C infinity. So it's constant from here, and you're matching infinitely many derivatives, but it doesn't have a convergent Taylor expansion there, because if it did, then it would have to look like this. An example of such a function is this. So it's piecewise defined. You can then, once you have the building block of a function like this, then you can play with it, scale it, squeeze it, everything. But the prototypical C infinity function, which is not analytic, and it's the bump function, is e to the minus 1 over x squared, right? This function is not defined for x equals 0. You can't plug in x equals 0. But I'm not even saying you should, because I only define this bit for x bigger than 0. And then I say that for the rest, I'm showing this function here. So for x larger than 0, it's a function which is like this. It's rapidly going to 0 when I approach x equals 0, because when I approach x equals 0, this goes to minus infinity. So this function is coming down rapidly. And when I push it forward, when x goes to infinity, then this is going e to the 0, which is 1. So that's why it's converging to 1. But of interest is this bit here. I took the first derivative here to show that it exists as a limit. Remember, the function doesn't have to be then, well, this function is defined actually. This is the second bit of the definition, is that to the left is just identically 0, including x equals 0 itself. So this function can be evaluated at each and every point of the line, because I tell you exactly what to do for every x value. It's completely flat, so all derivatives are 0 from here, and all derivatives are 0 from here, but it's not analytic. So it's infinity, but it's not analytic. Now it's not quite, this function behaves in the required fashion here, Okay, it does this, but then it goes to 1, so it doesn't do whatever I ask him here. But once you have this building block, like I said, you can rescale this, you can make this happen in a finite interval, you can squeeze a domain, but this is the type of connection that you want to play with when you build a function like this. So it's doable.
Professor?
Yeah.
Just a quick question. Why are we dealing with rectangular boundaries? Isn't it easier to work with circular boundaries, for example?
That's a good point. The reason why we're dealing with is that we'll be doing estimates on this equation and the component-wise estimates in the y and x direction. I'm going to get there for a second, because the minute we did this, then the estimates would not come out so nice. I agree with you that it's more appealing to work on circular domains. It's just technically this will be easier to do.
But you can't. So you can't use a circular domain in this case.
You could use, yeah, you could, but it would be harder. I'll get to that, because we will be working. There was a reason why I introduced these coordinates here, nice splitting in 2 directions, and with these choice of the bump functions aligned with these directions, the estimates will be substantially easier. Right?
Okay.
But there's nothing against what you're saying, right?
Thank you.
It's just, you're welcome, just practicality. Okay, so what does that buy me? So again, I will be passing to a nonlinear system, which I get by multiplying it by these 2 mask functions. So both for S and U, I will be taking these 2 right-hand sides here. And individually, I'm masking them with this multiplication. So I will do a bump like this, in exactly the same way I'm showing here in this direction, and also in this direction. Therefore, I can implement that by multiplying this either of the 2 right-hand sides by a psi function, which is supported over this delta, well, identically equal to 1 within the delta box and supported over the 2 delta box. And I do that in the ys direction and do the yu direction. I pull apart the 2 directions from each other. That will make it easier for me to do the estimates. One thing to note for the bump functions, I didn't say that all their, like I said, to make something go down really quickly is not a big deal. One can imagine to be able to do that. But to have control over the derivatives is a big deal, because when I modify a function with something that has huge derivatives, then that will change substantially, the flow map in between this region. And I still want to have control over that, because I want to have global estimates. Because here the system is still not fully linear. The masking function has already kicked in, but it hasn't fully removed the nonlinearity. And I want to have control over that function in this regime as well. So the big deal about bump functions is that derivatives, you can do this in a way that even though you're in a tiny domain, the derivative is still only some constant divided by delta. So it's not larger than that. It will be large if delta is large, because, hey, you have to make this happen this is of only order delta. So you have to come down from order 1 to 0. So you can't do much better than this, right? But you are guaranteed to be able to do it like this, that your derivatives are, for instance, not 1 over delta squared, which would be even larger. So that is the property of the bump functions that one can find. This is in books in analysis that do that. So when you have that and you want to estimate the derivative of your nonlinearity, generally for the general nonlinear system, that would be impossible to get a global estimate on the derivative of your nonlinearity, because who knows what will happen, right? But in the bumped system, just look, I take the derivative, this is shorthand for a Jacobian, right? Because these are both vectors, and I have S and U here because this is valid for both. So by the chain rule, that's the product rule, sorry. If this product the masking product is psi, then the derivative of this function is this prime's psi plus this times psi prime, right? So that's what I'm writing out here. Psi prime times the G, S, or U plus psi times G, S, U prime. For some reason, I swapped the order. Psi prime, I can estimate this as follows. I mean, first I have, this plus that. That's just a triangle inequality. And then since I have within each and every one of those, I have the product of two functions, then I just use the AB is less than A times B. So that will give me psi prime times the nonlinearity in norm plus psi times the derivative of the nonlinearity. Now psi prime obeys this estimate here. So I can upper estimate it by K naught divided by delta. And the nonlinearity globally, well, that's a little, not globally, but well, so here's the thing, that psi prime, of course, is only this large when psi is still active. After that, once I'm here, of course, I can do a much better estimate for psi prime. It's 0. So the psi prime, this estimate is a bit tricky in the sense that psi prime after a while is dead 0. So it's knocking out this term. So this is only not 0. This whole product is only non-zero inside the 2 delta box. But inside the 2 delta box, delta is small, I have a quadratic nonlinearity. I can estimate that from above as some constant times delta squared, right? Because that's a nonlinear term. Think of a Taylor expansion. Once again, globally, of course, I wouldn't be able to do this estimate for the nonlinearity, but I don't need to, because once I'm outside this box, psi prime becomes dead 0, so it knocks it out. So I will only ever have any finite magnitude for this product within that domain. And then I have the second term, psi from above, it's never larger than 1, so I write 1 as an upper estimate. And GSU, again, the same thing, is that psi, in fact, completely becomes 0 outside 2 delta. So this estimate is only a problem. It only becomes alive within the domain from -2 delta to 2 delta. So I'm basically in here. And in that domain, I can have a linear estimate in delta for the derivative of the nonlinearity, because this starts with quadratic terms. So its derivative starts with linear terms. That's why when I pick a large enough C1, I can do this estimate. And it will never get out of control, even though it's a general nonlinear function, because when it would start getting out of control and leaving the 2 delta neighborhood, psi completely shuts it off because psi becomes 0. So there's a cancellation here in psi. So make a long story short, the derivative of my nonlinearity is now globally on the whole phase space is bounded by a constant times the small number delta. Normally, I would only have this within the delta box for my original system, because the nonlinearity keeps growing. But with this modification, that local bound has all of a sudden become a global bound. Why is that advantageous for me? Because now I can globally apply the flow map to this differential equation. I don't have to worry about where I am. Am I in the box? Am I outside the box? Or wherever I am? And quite honestly, I don't know in advance where I'm going to be. But doesn't matter where I am. This estimate is always true for the derivative of the right-hand side of the nonlinearity. So that was the reason. And basically, this is the little picture of what happened. This was the original way the nonlinearity was picking up speed as I moved away from the origin, right? And who knows, it's going through the roof, right? Now, the masked nonlinearity is just the same as the original nonlinearity inside the delta box. But once I have reached the delta, this masking function will bring down my nonlinearity to 0, okay? And it will vanish. And that's why I was able to get this global estimate for the whole nonlinearity itself. In fact, it's a linear estimate. That's what I used here somewhere. Equivalent integral equations. Now, this is the other technique why I wanted to show you this. So this is the original ODE formulation that we have. And the technique that I just want to show you, if you haven't seen it before, doesn't require the system to be autonomous. It also works when the system is non-autonomous, okay? And the way it works is that here's your ODE. If you're able to split it in any meaningful way into a linear part plus the rest, and the rest doesn't have to be nonlinear. The rest can just be a crazy function, but you have to be able to pull out a linear term. That's the only thing here. So I'm not assuming anything at this point for this general reformulation for f, anything. And this is completely general. Then f has to be Lipschitz for this equation to have a unique solution. Formally, for a second, assume that you know the solution, just for a second, that you know this, and plug it in. When you plug it in, do that selectively. Only plug it in here. That sounds like a crazy idea, but if xt is really a solution, then any occurrence of x can be actually replaced by x of t, and the differential equation will still be satisfied just on that solution, on no other solution, but on that solution it will be satisfied. So selectively, I'm plugging in x of t here, but I'm not plugging it in here and there. What did I get that way? I got a differential equation, which is, I'm afraid, only valid along that solution, nowhere else. But I can, now this is an equation that I can formally solve, because what you see, this is a linear differential equation now with a time-dependent forcing. And we have a solution formula for linear differential equations with an inhomogeneous forcing. That's the variation of constants formula that we learn in ODEs. So why don't we not formally apply it with the understanding that this is only true on x of t? What's the variation of constants formula? It tells you have a homogeneous equation plus forcing, then the solution of that equation is e to the a times t minus t naught. EA is a constant coefficient matrix here, so this is the solution of the homogeneous linear problem. Applied to the initial condition at t naught times integral from t naught to t, e to the a t minus s times that forcing function. So that's what I used here. And now I kick back and I say, this is certainly true. And now I say, yes, it's only true for this particular xs of t. So I use the same notation here and there. So therefore, all of a sudden, you got a relationship for any solution. You haven't solved really the equation, because x of t, although there's a part that you know well, depends on itself through this. But it is certainly an integral equation reformulation of the ODE. And this is true for any ODE. That's why I'm showing it to you. If this was non-autonomous A of t, you could still do this, because we have a variation of constants formula for non-autonomous ODEs as well, except that it wouldn't be exponential. It would just require the fundamental matrix solution of that linear ODE. But the same trick would work. You would use the fundamental matrix solution here and there, and it would transform the system into an integral equation. And this is the general idea of the Lyapunov-Perron reformulation, to transform the original ODE into this equivalent integral equation, right? It's not a solution, because x of t is here and there as well, and its initial condition is here. But this turns out to be substantially easier to work with, because you can do all of a sudden estimates on x of t, which will involve estimates on the right-hand side. And if you know a little bit about f and you know about the growth rates here, you can actually get surprisingly far. So let's apply then this reformulation to start, which is our ODE. Where's our ODE? Here. So this has the same structure, right? Because it has a known linear part, plus it has this unknown nonlinear part. Let's do this equivalent reformulation in terms of an integral equation. And this is it. So this is why I use the two components separately from each other. This is now a diagonal matrix here, right? Because I have picked a linear, A is diagonal, therefore this is diagonal. So it will be, this is e to the t minus t naught. Here's another trick. In principle, nothing stops you. That if you have several equations, then write this out as several different scalar equations, think of them. And the minute you do that, each and every one will have a t naught in that equation. But nothing says, when you then kick back and say, nobody says that it has to be the same t naught for all of them. Certainly not in an autonomous setting. This would bring in complications when you have a non-autonomous setting. If this was A, was a a time-dependent matrix. I ran out of juice, sorry. I have to talk for a while until it recharges, but just a few seconds. So this would have an issue if I try to do this for a non-autonomous system, but I have an autonomous system here. So surprising as it may sound, in the different equations, I can pick initial times that are different. Let's see, what's my charge level now? It's 6%. Let me just wait a few seconds. If you excuse me, I'll drink the rest of my coffee. It's 7% now. Okay, so just imagine once again that here normally I would have T naught. Okay, I would have T naught here. I would have T naught here, and I would have T naught here. Okay, this is okay. But then I can stare at these equations sort of individually. I would also have T naught here, T naught. Just look at one of them, and that remains true by itself. And just for that one, I can just pick one particular initial condition, initial time, and for the other one, I can pick another initial time. And I can do that fundamentally because the underlying equation is autonomous. It was autonomous, so its solution will not depend on that. So my point of reference so the reference time doesn't matter. So note the difference. So in the y-s coordinates, I'm starting from TS, and the yu coordinate, I start from TU, but that's just the initial time. The same here. I'm not changing the actual initial conditions, not at all. It's just that my reference to the initial time is different in both cases, and that the initial time will appear in there. So that's one thing to know that I should highlight. TS in the first equation, and T naught goes to TU in the second equation. So there are these two surprising steps, but you can do that to any equation. I'm not using this particular form. So why is that so? Because with that different choice, I will be able to play with these initial times in a way that eliminates some of the terms in these integral equations, and then will make estimating the solution easier, because ultimately I want to estimate these two. Why do I want to estimate these two? Because remember, the way I defined my local stable manifold is all about the evolution, which this is here y of t, right, norm. It's all about the evolution of these being bounded in time forever or not. That's why I will take a keen interest in understanding how these guys evolve in time, because they are components of a solution whose norm will be a matter of life and death, right? If it remains bounded, it's in the stable manifold. It becomes unbounded, it's not in the stable manifold. So here's now the first sort of benefit from separating the two initial times from each other. If ys and yu launched namely at these different reference times, but it really doesn't, it's still the same point. If it's in the stable manifold, and if that stable manifold is not empty, hopefully, then let's look at this term here in the second integral equation. All I'm doing, I'm rewriting that term here. Okay, so keep in mind, I'm working on this term. And let's just rewrite it. I can use the properties of the exponential e to the lambda u times t minus t naught, tu. I write that as e to the lambda ut times e to the minus lambda ut, right? All I did, I wrote this as a product. And that still multiplies yu at tu. And here comes the observation that yu at tu as tu goes to infinity. See, this is another trick that's, I don't know, people that developed this came up with all these tricks, but But it's amazing how they work in the end. You could say, wait a second, I had a statement about what happens on the stable manifold in terms of these guys being bounded in time for all times. But this is not that time. This is the initial time. That's not the t. But then I say, yeah, but it's still a time argument that I can take and shift, and the solution will react accordingly if I start changing the initial time. It's an autonomous system. All it serves is just tell you where you are along the solution. So why don't we take this initial time, just for the heck of it, formally, to plus infinity? So interestingly, I'm not changing the evolution along the trajectory. I'm just repositioning the initial time the way I denoted the initial time. So then what that means is that when I take this to plus infinity, then since I am on this set that I have envisioned for myself, and on that set, the trajectory remains bounded for all positive times uniformly by a k. Remember, that was our definition of the stable manifold, right? This is what it says. It basically, I'm acting on of the solution operator on y naught. And when I take that, this is, don't forget, this is just y of t, right? So y of t, oh, that's the, I'm sorry, I'm showing this on the wrong definition. That's still y of t, that's not, it's not, I meant to show this here. That's the norm of y of t. It remains uniformly bounded as it doesn't matter how large the time is, how large positive time is, right? This is how I was looking for the stable manifold, that, you know, it doesn't give in to this trend, but it remains uniformly bounded. I'm not saying what that bound is, but I'm just saying it's bounded. And that's good enough here, because if this remains uniformly bounded as I push its argument to plus infinity, which happens to be the initial condition, but that's but that just tells you where you are, then this remains uniformly bounded on the stable manifold. But it also gets multiplied by a term, which then rushes exponentially to 0 as I do this operation, tu rushing to infinity. So you have something that goes exponentially to 0, and then you have something that remains uniformly bounded. And then all this is multiplied by something in which, funnily, time is now fixed, because time is not ticking. I'm playing with the initial condition. Long story short, this is a constant then, because time is fixed. This is running to 0 exponentially fast, and this is bounded. So the end result is that this goes to 0, because this term just overpowers everybody else. So if I position myself that tu is taken to plus infinity, this term is out. So why don't I do that? So I change this to plus infinity, and then this term is out. And this is what you get here. So it's the same integral equation, except now I said, let's push tu to plus infinity. And you know what? Ts, I'll just, out of convenience, that was the other initial time, I pick it to be 0. And I can do that because this is an autonomous equation. So it's a major simplification. It turns out in the estimates that at least the second equation, even though, now mind you, this has become an improper integral, but it turns out that's okay. It turns out that this has the right properties, and precisely when, excuse me, when approaching this bound, this will exert its control and decay exponential. So it will make this integral converge. I lost one term, so I'm better off doing the estimates. So this is yet another form of the integral equations. And this is now, however, it's only true on the stable manifold. So because I used the definition of the stable manifold to make this argument. So whereas this was true for any solution, this is no longer true for any solution. In fact, it's only true on the stable manifold. And I don't know if there's a stable manifold. So I have to show that this integral equation actually has a solution. But mind you, whereas here, I knew that this has solutions. In fact, it has lots of solutions because it's equivalent to the original ODE. Infinitely many solutions. This now doesn't have infinitely many solutions. In fact, it's a priori clear if it has any solutions after I've tinkered with it. But if it does have a solution, then that's my stable manifold. Okay, so it will only that I have zoomed in on solutions that are on the stable manifold. And the way people deal with this is that they now say, all right, so this is obviously I can't solve this equation directly because I have the unknown occurring all over the place, but I do have a sort of a semi-explicit expression because a function of the unknown gives the unknown back, except that function is a non-local operation. It involves the whole, you feed it into a nonlinear term, weight function, integrate. So it's a non-local operator, but it's in this general form that there's an operator acting on the solution, and it gives me the solution back. It also depends on a parameter, which is this, and that's the only parameter that I have, is the initial condition for the ys component. And then just to show you what that is, it's this. So basically, once I have picked a delta box, even if I have something like a stable manifold, which I don't know at this point if it connects to the origin or not, I'm just hoping that there's a set of boundary trajectories. What I label it with, hopefully, is its intersection with the box. If I change the box to something smaller, I still only hope it for a unique intersection, but this will change, this point of intersection. So that's the only parameter, so to speak, that's here. Do I need to worry about that parameter? No, because in fact, I was showing it in this direction. I was wrong. Ys is the stable direction. So it's really just delta. I'm just delta away from the origin. So once I have picked the size of the box, then the x component of that initial condition is given. And that's what you see here in the stable direction. This is it. So this will be just conveniently delta if I'm on this boundary and minus delta if I'm on this boundary. But it's still a parameter. But I have changed it already here to delta, which means I placed myself on this boundary. So basically, this becomes a fixed point problem. You have a general non-local operator acting on a function subject to this parameter, which is simply the size of my construct, this delta, and it should return the same function. And if that happens, then because of all the steps that I've taken, that will only happen on the stable manifold. If this integral equation, this operator equation, this nonlinear operator equation has a unique solution, then I have a unique stable manifold. So how do you go about that? When you have equations like this, the theory of equations like this is very well developed because it basically, people have spent a lot of time in developing what are generally called fixed point theorems. Because a solution of this equation is a fixed point of this generalized operator. And one of the most, perhaps even the first one, if I know, was the contraction mapping principle, which unfortunately now I forget, but it's not even that old. I think it's in the, I risk now being wrong, but I think it's perhaps 1920s, 1930s or something. It's not that old, right? And it's a surprisingly powerful and simple statement that becomes applicable here. And you may have heard it in other classes, but some of you may have not, and that's why I'm going through it. So the objective to show is that you have an equation like this that has a unique fixed point. I'd like to show that. And there's a general principle that would assure me if I can verify its conditions. And this general principle, which I'm listing as an aside, is the Banach fixed point theorem, which I think is from 30s, but I'll look it up next time. Hopefully I'm not wrong. You know, first, I think my recollection is first half of the last century, very first. And it's surprisingly simple, and it has really revolutionized nonlinear analysis in many different ways, although it's surprisingly simple. It says that if you have an operator like this, a general operator in a complete metric space, so what's complete? It means that every sequence that's a Cauchy sequence, which means that you check adjacent elements and they sort of get closer and closer to each other, right? So there's accumulation in the sequence. So every Cauchy sequence should converge to a point in the space. So think of closed sets in Rn, which are by themselves complete metric spaces. An open set would not be, because you can select a Cauchy sequence that's marching towards the boundary of the set. It would converge on the boundary of the set, except that the boundary is not part of the set, right? So open sets are not good, but generally speaking, anything that is closed in a metric, so all Cauchy sequences converge, is good. So it's a complete metric space. Metric just means that you have a scalar valued function defined on it, which is satisfies the axioms of a distance. Symmetric, and it's non-zero or non-negative, and it only is zero if the two arguments that you feed in are are identical, and it satisfies the triangle inequality. And again, a thing to think about, which is not a complete metric space, is just an open set in R squared. But this is completely general. It's an abstract space. So that the beauty of this isn't, you don't have to think about a subset of Rn, but it's just any part of a function space, any space of objects on which you have a metric and which is complete in that metric. So the power of this theorem is that powerful. It applies to anything like that. And the only assumption in this contraction mapping principle of Banach fixed point theorem is that F is a contraction mapping. And that's, again, a simple concept. It basically tells you that you take any two elements of that space. And again, these two maybe matrices, operators, functors, functionals, whatever. And as long as in the metric that you have, the operator, when you apply to these points, shrinks distances, then it's uniformly, it's called a contraction. So apply the operator to two arbitrary selected elements of the space, measure the distance of the outcome, and it has to be less than or equal to a factor q times the original distance. So that means that you're shrinking the distance. And the shrinkage must be uniform. So this q must be, so first of all, it's uniform, it's valid for the whole space, and q must be between 0 and 1. So that disallows keeping distance, because q is strictly less than 1. So even when you have equality here, you have been shrinking distance by a factor less than 1. So this is what it means for a contraction, for an operation to be a contraction. Take any 2 points in the space, apply the mapping to them, and wherever they go, the output distance is always smaller by a uniform factor. Then F has a unique fixed point in B. Okay? So if I'm able to establish that this mapping that we had here, although a lot of the details are fuzzy, I don't know the solutions, but if by and large I have estimates that show me that if I feed in two different curves and I then watch what the outcome is, then generally speaking, what I have fed in is not going to be a solution to this equation, but there will be a solution, and the solution is unique. So very quickly, maybe I get started on how you actually show this, because I think this is part of the beauty of this proof, because once we have this nailed, then we're almost done. We just have to do estimates to show that it's a contraction mapping. And the Banach's proof was so simple. I don't know if this is his original proof, but it's amazingly simple, that you basically, it's also, the proof is constructive. So basically build an operation. How you prove this? Just start from any initial condition in that metric space and start applying this operator to it. So x0 was your initial condition in the metric space. This is your first iterate. This is your second iterate. If you were to estimate the distance that you have on that space between your nth iterate and m plus first iterate, okay, then remember that xn you just got by applying this operation to xn minus 1. I think there's a parenthesis missing there. Okay. And you got xn plus 1 by applying this iteration to xn. So all I'm doing, I'm just building this sequence of points, and I'm checking the distance between two adjacent ones. But that's just this, because I got those points from somewhere. I applied them to earlier versions. And then I use that this operation F, this mapping, is a contraction mapping as assumed. And therefore, I can write this distance as q less than q times where I started from as arguments. So this the distance of this and that. So this is where we're using the contraction property for this mapping. But then this shows that out of this iteration sequence satisfies the definition of a Cauchy sequence. Because look what I'm getting. I'm measuring the distance between two adjacent members of that sequence. And what I'm finding is that it's shrinking along the distance because it's by a uniform factor smaller than the previous such difference in the same sequence, right? So the distance between xn minus 1 and xn, these are the xi's, gets shrunk by a factor of q when you apply the iteration here. So it's a Cauchy sequence. That this means this is the distances are decreasing in the sequence. And here's where it's crucially used that B is a complete metric space. Otherwise, it wouldn't work. And I still remember I've seen complete baloney things proven in papers where people have skipped this step. And they were using the contraction mapping principle on an incomplete metric space. And I just said, how are they getting this result? It's clearly wrong. And they said, oh, no, it's just the contraction mapping principle. It's trivial. We leave the details out. I mean, everybody knows the contraction mapping principle, right? Yeah, but you still have to check its conditions. And they didn't check it was a complete metric space. And they were claiming a unique solution to a problem that clearly didn't have any, or maybe had multiple, I forget. So this is a crucial point that this Cauchy sequence therefore stays in that space. And therefore, the Cauchy sequence will have a limit. So this blindly started iteration, which a lot of people do in engineering practice a lot. I mean, I learned that first in that principle in undergraduate courses, that you don't know something, you just start iterating it. You apply an operation, look what comes out of it, again, feed it in, right? Does it automatically do that? But that can generally lead nowhere. However, if it's a contraction mapping, then it not only does it lead somewhere, but where it leads is also unique. So we know that it has a unique fixed point based on these principles. And it only remains to show then that since f is uniformly C0 continuous, and that comes out from this, this is a stronger form of continuity for the mapping with a uniform index, then if its argument converges to a fixed point, then the function itself must be converging to its value at that fixed point. And from that, it just comes out that the function at the fixed point is just the value of the fixed point itself from these two. And there you go. That's exactly what we were after. So this, I keep using fixed point, is the limit of this Cauchy sequence that we know exists in the space is automatically a fixed point for the mapping. And then the uniqueness is just one line. Can I have, all right, this establishes that I have a fixed point, but can I have two? Assume that I have two different ones, that they are not equal. Then you simply apply the contraction mapping principle. You take either of those and feed it into the mapping and measure the distance of the outcome. Now, because they are individually fixed points, fx star is x star and fy star is y star. So this difference on the one end is just the difference of x star and y star, which are two different fixed points. However, now you apply the contraction mapping principle that says that, by the way, this outcome distance must be less than or equal to q times the distance of the two fixed points. Unfortunately, however, q is strictly less than 1. So these two statements are contradictory because this cannot be, so this and that are completely equal, and it would equal or not equal, right? So they're equal. So it would seem to imply that this distance between the two fixed points is less than q times the same thing, less than or equal to, but q is strictly less than 1. So this cannot hold unless the distance is 0, when both of these are 0. So the two fixed points are equal. So this is the proof of it, and this really has revolutionized nonlinear analysis. This is how people now prove existence, not just invariant manifolds, but existence and uniqueness of solutions to ODEs, PDEs. They reformulate them as integral equations and use the contraction mapping principle. So I'm not quite done yet, but I'm mostly done. So tomorrow I'll just finish up this proof because this was the heart of it. We just need to show that this mapping that you see, the right-hand side, apply to Y, and it spits out Y again. That's a contraction mapping on a complete metric space. When we show that, we're done. And that only involves, it turns out, estimates. So I'm done for today. Any questions?
Yep. Again, this may be a bit far-fetched. I was just wondering that, so for the better part of this strain of thought, we have been exploring how to find a stable manifold which goes through a saddle point, right? And I was just wondering if maybe this is just the lack of my imagination, but are there any real cases in which manifolds like this matter? Because a stable, it's something, if you don't go from the right direction, it will just pop you out of it and you will never see it, right? So you have to be on that track very early, and it's a very low probability event for us to end up on this manifold, right?
Yeah.
And are there any relevant examples in which these are something that we should take into note, and we should?
That's a good point. So you being on the stable manifold of a saddle point is a low probability event. Absolutely.
Yeah, and it's very dangerous to be on there, right? Because any disturbance that I'm going to get thrown out,
exactly,
and the plane crashes and whatever.
Right. That's true. But it's a very good point. There are multiple examples in which that's important, because the global stable manifold, if you think about it more globally, it's a watershed. It decides between two different behaviors, whether you're going to go this way upwards and maybe end up on a limit cycle, or go the other way and end up on an invariant torus or chaotic attractor or any of that. Okay, so there are multiple examples when you try to piece together the global phase portraits. Then these measure zero sets, because they are watersheds, they are basically controllers of different global behaviors, they become very important. And for instance, you were perhaps not taking the first part of this course, but if you looked at the material, we were computing finite time Lyapunov exponents to understand global behavior. And the finite time Lyapunov exponents highlight the stable manifolds or saddle points as dividers. And they say, oh, if I'm on this side, I go this way. If I go that way. So for instance, in fluid mixing, they're incredibly important in that sense. But also there could be things that live on the stable manifold. For instance, you can have an unstable, in a more higher dimensional setting, you can have an unstable limit cycle which is contained in the stable manifold. And that limit cycle has also things sticking out of it. So whereas you're absolutely right that us being on the stable manifold itself has a zero event, but the manifold itself has such a global significance that it divides regions of different behavior. That's why we think it's important.
Oh, thank you for the insight. So it's the division that matters, and not that
exactly. Exactly. I will also say that we say this because the remaining directions are unstable, but in the remaining time of this course, maybe the next week and the week after, I'll talk about cases when you have a stable manifold within which you have other stable manifolds, right? And all of a sudden then slower stable manifolds, and all of a sudden they become very important. Because in the remaining directions will not take you away, so you don't have that stability, but still this is a measure zero thing, but it turns out to be very important for reduced order modeling, because you get very close to it, even though you're never on it technically, right? You get very close to it.
Oh, thank you.
Yeah, welcome. Anything else? Feel free to ask questions. All the questions I'm getting always very good, and especially when sometimes I don't even, I'm thinking, and since the writing is so small, it's harder to notice the mistakes. Sometimes on a blackboard it's easier, and the mistakes usually come from the fact that I write something, I say something. Why I'm writing that, I'm already thinking about the next thing, and then I inadvertently write what I'm thinking about. Okay, so feel free to ask questions. Anything else? Okay, looks like we're done for today. So see you tomorrow. I'm going to finish the proof tomorrow and maybe get started on another subject. Have a good evening.